Okay, good old Borat here. So we've got two electrons and two positrons, and the first question asks for a full description of the potential here for dipositronium. So we've got two electrons, E1 and E2 there. That's Clarissa and Juan, negatively charged. And then we got two positrons, E plus A and E plus B. I think we're calling that Clarence and Julia. And so the interactions, they're going to be pairwise interactions between all these things. So there's four pairwise interactions that have opposite charges, and the distances are RA1, RA2, RB1, RB2. And then there's some cross reactions between the two pairs that have the same charge there. There's an R12 and an RAB. So we put all this together, and we've got plus 2 Rydbergs times, and then there's -1 over each of those negative charges, opposite charges, R1A, R1B, R2A, R2B. And then there's the positive terms, the repulsive terms, plus 1 over RAB and plus 1 over R12. So that's the first part. That's pretty straightforward. And now the hard question, the hard part of the question is, what does the thing look like? What's the bond distance, and what is the energy? And remembering that for positronium, in the end, instead of -1 Rydberg as we had for a reduced mass of a 1 electron mass, when we went to positronium, we got to an energy of -0.5 Rydberg. So basically the issue here is whether this thing is more like helium or dihydrogen. And the answer is it's more like dihydrogen. And the reason is that helium gets its big break in terms of a lot of negative energy by having the two positive charges of the nucleus be right on top of each other, and that is not going to happen in dipositronium. So what we have is we have interactions, and each interaction looks like an energy that can get down to as much as -0.5 Rydberg, but it's got a characteristic distance that is more like 2 times the Bohr radius, so something like an angstrom interaction distance, because the distance is spread out compared to hydrogen, neutral hydrogen atom, which is a 1 Rydberg characteristic distance, but we have a smaller reduced mass here, and so the thing sits up higher in the well and has a characteristic distance of more like 2 Bohr radii. So that's one piece, and then even though so the key thing here is, I mean, what is a bond distance? There's no real nuclei. The positrons and the electrons are identical except for charge, and they've really got to look identical in the ultimate situation here. There's these negative terms, the positive terms are plus 0.5 Rydberg basically, and the same. Those potentials have to look the same. There's 4 stabilizing interactions. There's 2 destabilizing interactions, and so in the end, the thing is going to form a bound complex. There's more attractive interactions, twice as many as there are repulsive interactions. So it is going to have some sort of bond in there, and the question is, how do we figure out the distance, and then how do we figure out the energy? And well, the distance comes from thinking a little bit about the wave function. So there's got to be some interaction distance, and the mean distance between the two electrons actually has to be the same as the mean distance between the two positrons, because we can't tell the difference between them. Well, we can tell the difference with charge, but they're otherwise totally identical. And so the exchange wave functions, again, for the electron with electron, Clarissa and Juan, or the positron with the positron, Clarence and Julia, are going to be the exchange wave functions that we're used to looking at. And so there's either going to be a symmetrical exchange wave function or an anti-symmetrical exchange wave function. And those interaction distances for Clarissa and Juan and Clarence and Julia are each going to be maybe 2 Bohr radii as a characteristic distance. So the best guess is that's what we would call a bond length, is that maximum, the expectation value of the average distance between the objects of like charge, because those are the analog to a the regular bond there. So the best guess for the energy, it's going to be something like half the energy of hydrogen. Could even be only quarter the energy of hydrogen, because the greater distance, effective bond distance, might even make it a little longer. But probably half, two Bohr radii is roughly an angstrom. That's roughly the same bond length as in hydrogen. So the reduced mass is going to wind up raising the overall energy, and it's going to be something like 15,000 wave numbers. Minus 15,000 wave numbers is the energy. The bond strength is going to be about 15,000 wave numbers. But that's the key here. I mean, this is conceptually hard, but you have the pieces to figure it out. This is supposed to be the challenging part of the question, and the key is there's got to be some sort of exchange wave function for the electrons individually and the positrons individually, and they actually have to be, the two of them have to be basically the same. So now we ask, what does the actual wave function look like? And we actually had to get fairly far into that by just thinking about the mean interaction distances up there. But the thing here again is that we have to describe both the electrons and the positrons. And like everything else, we always express these overall wave functions assuming some sort of separability. And so we're going to try to multiply an electron-like wave function, phi e minus there, with a positron-like wave function, phi e plus. And again, the key here is that the electrons and positrons are basically identical, except they have different charges. And so those two wave functions really have to look pretty much the same. So we're going to call that as an overall wave function. Each of those two wave functions are going to look like, this is an H2-like system. And so there's going to be a sigma type wave function, and it's going to be a sigma Gerada 1s, a 1s A plus a 1s B wave function for the electron, and then we're going to multiply that for the two electrons. We're going to multiply that by another sigma Gerada 1s wave function, looking just like the H2 wave function, but this time that's describing the probability distribution and energy and everything else of the positrons. So we multiply those two things together, a sigma Gerada 1s for the two electrons and a sigma Gerada 1s for the two positrons, and we get our overall wave function. So we managed to put four charged objects into sigma Gerada 1s orbitals, if you will, because the positrons and the electrons are individually somewhat separate from each other. Their motions are on the same timescales. We cannot and do not have any sort of Born-Oppenheimer approximation here. We just have an overall wave function that describes the whole schmear of these electrons and positrons. And so that thing is going to look like a singlet sigma, because we have the two electrons, and they have to be anti-aligned in spin, the two electrons with each other. So that's a singlet sigma state. And then the positrons also are going to be in a singlet sigma state. And so, again, those multiply together to get an overall wave function that's going to have singlet sigma character. There's no orbital angular momentum about any z-axis or anything else. There's only one way to do it. The electrons have to be up and down anti-aligned with each other, and the positrons have to be up and down anti-aligned with each other, and we get the overall singlet sigma wave function. So overall, the thing is going to look like our favorite sort of circus tent sigma Gerada wave functions there for the bonding sigma orbitals. We're going to have two electrons in that, two positrons in that. Those are two separate wave functions, the electron wave function and the positron wave function, but they do tend to place the electrons and the positrons in the same basic place. So the two tick marks are if you will, the most probable nuclear locations. And since the electron and the positron both have that wave function, the electrons and the positrons are trying to be close to each other, unlike the exchange wave function for the electrons with respect to each other, where the probability of finding them exactly on top of each other is 0. Here the electron and positron do their level best to be in the same place, so that's the wave function still going to peak there, but they're both light and fast and smart, and they're moving around a lot, and so they don't ever really get to do that. That again is why this thing doesn't wind up looking, it's why helium is not a good analog, because the two positive charges in the helium nucleus, they stay put. The two positive charges associated with this dipositronium are smeared out just like the two negative charges. And so there is a higher probability of finding one positive charge and one negative charge near each other. But the other positive or negative charge is not going to have anything to do with that, because it doesn't have any energy advantage to being close to a negative charge that's sitting right next to a positive charge, and it doesn't really help out very much. So finally, what goes on with the first excited energy level? And this is really important to get full credit here to talk about both the positron and the electron. So again, this is an H2-like system, so the excitation for H2 is to excite from the sigma Gerada 1s one electron to a sigma Ungerada, the sigma star 1s. And the key here is we can do either a positron or an electron, because they're basically the same thing. So we can pop either one of those two into the sigma Gerada, sigma Ungerada, into the sigma star, and have a 1s, a sigma Gerada 1 electron, sigma Ungerada 1 electron, times leaving both of the positrons in the sigma Gerada, or we can have a sigma Gerada 2 electrons, and we can have a sigma Gerada 1 positron, sigma Ungerada 1 positron. So either one of the two of those can get excited. And so the overall wave function there in the first excited level is going to be and once again, it'll be a triplet once we go into the sigma star, because the triplet for either the electron or the positron is going to be the lower energy. It always is. The same exchange issues apply here. And so there's going to be a triplet that consists of a triplet in the positron, basically, or a triplet in the electron. We can have either one. It's an or, which means there's three states for the triplet associated with exciting the positron, one of the positrons. There's three states with a triplet, associated with exciting one of the electrons. And so overall, the degeneracy of the system is 6.